Everybody in the AP Chemistry series. Today we start with part 2 of section 8.1, which is all about introductions to acids and bases. So generally today we'll start with a beautiful concept that it has so many applications in our real life, which is the pH scale. And I'm pretty sure that you've used this before or heard about this before. So the first definition of the pH is a measure of the H positive. So we just remember the acids are considered as a substance that produces H positive ion, or it has another name, which is the hydronium ion. Let's start over how to calculate the pH. The pH has a beautiful formula to be applied, which is negative log the concentration of hydronium ion, or H positive. So for example, if you want to do that on your calculator, you have to press on negative and then use the log with the base 10, just keep in mind, and then you put the concentration of the hydronium ion. So let's take an example like applying that in real life. You can use your calculator right now. So if I want to calculate like 1 times 10 to the power 0, just notice any like number that is raised to the power 0 is equal to 1. That's going to be the log of 1. And based on the algorithms rules, rhythm of 1 is equal to 0. So we can see that the pH now is 0. Okay? Okay. Now, if we want to take another example of calculating the pH, let's say negative log of a concentration of 1 times 10 to the power negative 2. If you apply that in your calculator, you will end up with 2. So the question now, is there any relationship between the power and this number in here? The answer is yes. But when do we have the same power with the same pH? If the number that is multiplied by 10 here is equal to 1. So for example, if we come here to this table, we're going to focus on the concentration of H3O plus only at that moment. So you just notice that the power here is negative 1, then the pH is 1. The power is negative 2, then the pH is 2. The power is negative 3, and the pH is 3. But there is a condition in that. You never have these numbers until you have the number to be 1 that is multiplied 10 to the power something. All right. We have to study one more thing. Just keep in mind if you have, let's say, an acid. My question now, if you have the concentration of pH of 0 and a pH of, let's say, 4. And my question is, which of these pHs represents higher amount of H3O plus? For sure, you're gonna say like, since the pH here is 4, then it has higher concentration of H3O plus. But it's wrong. You have to keep in mind that the lower the pH will be the higher concentration of H3O plus. So among these beautiful concentrations, we can notice that the pH of 0 has the highest amount of H positive and the least amount of acids as represented in the concentration of 10 to the power negative 6, or pH number 6. Let's talk about another concept, which is the pOH. It's the same idea as the pH. Since here in the pH we're describing the concentration of H positive, if I want to measure the concentration of OH negative, I have to take the pOH. As we said, you can see that the P letter here represents negative log, and then you put something inside. Let's have an example. And here, if I have a concentration of, let's say, the OH, 1 times 10 to the power negative 8, then how can I represent that in terms of the pOH? How to calculate the pOH for that? So it's the same idea that was done for the pH, and it's equal to negative log, you put the OH inside, and then you will have, since the number here is 1 and it's multiplied by 10 to the power negative 8, then the pOH is equal to 8. All right. One more thing to be discussed again about the pH scale. We can notice that the pH starts from 0 to 6, and it represents the acidic environment, or the acids in general. So these are for acids. Okay. And from 8 to 14, it represents the bases. And you'll ask me, what about number 7? Number 7 represents the neutral solution. The last point of the pH scale is the higher the pH will be, the more basic. For example, we said that the basic solutions start from pH 8 to pH 14. In my question, if I ask which of these bases you expect to be the stronger bases in here, so the one with 14 will be stronger than the pH 8. On the other hand, it's the opposite verse, at which the lower pH will be more acidic. So we can notice that 0 here is more acidic than pH 6. On the other hand, the pH 14 as a base is stronger and it's concentrated more than the pH of number 8. There is a beautiful concept that is called autoionization of water. So from its name, it means that the water itself will start to dissociate and split up. So as we can see, look at the figure, you have two water molecules. This is water molecule 1, this is molecule 2. You just notice that as a result of this dissociation, one of the hydrogen is moved to the other water molecule. And as a result of that, two ions are produced as a result of transferring the proton, which is H positive. So the water molecule that gained a proton becomes H3O plus. The one that lost a proton becomes OH negative. So if we represent that in terms of an equation, we can say that the water, you have another water molecule, they're reacting with each other. You can see that this is a reversible reaction that is favored to form more reactants. It gives H3O plus in addition to the OH negative. And we can see that this is aqueous, this is aqueous, and these are, for sure, these are liquid. And now from unit 7, if I ask you, since we're in equilibrium, how can I represent the equilibrium constant? And you can say, okay, the equilibrium constant represents the products, the concentration of products over the concentration of reactants raised to the powers. And we said that we ignore the states of solids and liquid. So since we have aqueous and aqueous for products, we can say they're equal to OH negative multiplied by H3O plus. At that point, we neglect water as it's in a liquid state. So we can say, okay, the equilibrium constant at that point is equal to the concentration of hydroxides and hydronium ion multiplied with each other. And since we're talking about water, like this is a property of water, we can say this is K and W, which stands for water. All right, so the Kw is equal to H3O plus multiplied by the concentration of hydroxide ion. All right, one more piece of information that will be given to you. We're talking about splitting of water molecules. We're talking about dissociation. And I thought, what you think that this process needs energy. In other words, we can say that this reaction is endothermic, which means I need to supply the system with the amount of heat in order to proceed. So since the reaction here is endothermic, I mean the auto dissociation of water, it needs energy. Now from unit 7 again, we're going to go back so much at that point. If I want to increase the temperature of my system, based on that, the reaction will be shifting to form more products. And forming more products means that the Kw will increase at higher temperatures. Let's just have a look at this beautiful table in here. We can notice that this is Kw, so we can just notice that the Kw differs at different temperatures. So it's increasing. The Kw increases as the temperature increases because, you know, like the flow reaction is endothermic.